All right, so what I want you guys to do as we go through this notes is I'm going to have you just read it on your own because I wouldn't want to just read it out loud to you. Um, Go through this in your packet, fill in the notes, and then, I'll put pop-up questions as we go, okay? Let's go and read that. Okay, next one. Pause if you have to on the video. Okay, so now what we're doing is we're going to be proving SAS. All right, so we're looking at these two triangles, and we need to prove that SAS works. Okay, and we need to do that by discussing transformations. You see that's in here. So read this out. Okay, so how can we transform this to get to the B there? I'm sorry, how can we transform ABC so that it lands on DEF? Okay, so now I want you to remember back how when we transform something, when we first talked about transformations, we would name that new triangle prime. Okay, so ABC prime. Okay, so that new angle becomes prime. So it'd be A prime, B prime, C prime, right? So if we move them, we want to know, are they going to be equal? Are these pairs of angles going to match up or correspond? Okay, so this is all in your notes, so we're just kind of going through this. So now again, well, what if we rotate it? Okay, so it says, well, if we rotate it, okay, so if we translate it, so that would be A prime, ABC prime, and then rotate it, that would be ABC double prime, right? Okay, so now all this is what this is saying is just that, when we move it, this angle should be equal to D, this side should be equal to DE, and this side should be equal to DF. No matter what, because remember, rigid transformations do not change anything. Okay, so now if they also preserve angles, because remember, if we rotate it or reflect it, it's still good. Angles don't change. That means that this angle is equal to the angle after you've moved it once, BAC prime, measure of angle BAC prime. And after you rotate it, the second transformation, and measure of angle BAC. Okay, so that just means that it doesn't change. It doesn't change when you transform it. That's essentially what this is saying. Okay, so that we know that AC is going to be equal to DF when we move it around. Okay, so let's move on. Okay, so you use the E tool to kind of figure this out. So here, if we first translate it, and now we're going to rotate on point D. See how he clicks put the point on point D, and now we get it to line up. Okay, so basically it's a translation and rotation. Okay, and the E tool does a better job of showing it. Okay, all right. Now what about these triangles? Okay, well here we've got side, angle, side, angle, sides. What kind of transformations would we need here? Well, you can use the E tool for this if you want to check it out. Okay, so notice how this side doesn't really look like it corresponds with this side, right? Because that's 2 and this is 1. So what could you do to get them matched? Flip it, reflect it. Now they do match. And then lastly, translate. Okay. So again, you can do that with the E tool, see the same thing, little rotation, little reflection, boom, you got it to map up. Equal. Okay. Fill that in your notes there. Okay. All right, so now you proved, as we talked about SAS, okay, by looking at those different triangles and showing that no matter how you move them around, they'll still be equal. Okay, now let's look at ASA. Okay, so now we've got angle, side, angle. Okay, so again, what types of transformations would move this to there? Okay, and we need to show that as we move it, A will still be congruent to D. AB will still be congruent to DE, and B will also be congruent to E. So that's the main thing we need to prove. Okay. Well, we can translate. Genesis, we can translate and then rotate. Okay. And she says rotate on point D. Rotate the triangle so that point A lies on point D. We've got to rotate so that these match up. Okay, and point B lines up on point E, right? Except this time we don't know either AC, this side, or we don't know whether AC is equal to DF. So how do we show that point C, this one, is on point F? Okay, so we have to prove that. Well, first we translate it and rotate it. Okay, then we can get into line up. So through the rotation, through the translation, we show that those points do line up. So that's kind of our proof. So she thinks for a bit, okay, I think E is congruent to B. How can she be sure? Because the rigid transformations don't change the angle size, so they will be equal. Okay, so Patrick points out, well, this means that BC, this side, is identical to EF, right? Using the same reasoning. It doesn't say it's equal, but if we're using the same reasoning, that when you rotate it, it should be right. Is he right? Not necessarily. I'm sorry. Yes, he is. Okay, rotate again. Rigid transformations don't change angles. Okay, so then she says, well, that must be it. It must be congruent because point C is on point F. Okay, so we'll go ahead and fill this in. I'm not going to go through all that. Just read it. Okay. All right. Eddie asks, what if we need a reflection to have triangles lying on top of each other? Does this affect the result? Again, no, because rigid transformations do not change angles. Okay, fill that in there. Okay, so now let's look at AAS and HL. Okay, so we already looked at ASA and SAS. So we have angle, side. Okay, so let's take a look at what's going on here. Okay, so the question is, how can a triangle that has two congruent angles in one side be also angle side angle? How could that be? Well, if we take a look, let's say that's 120, that's 40, right? Well, could we find this a third angle? We could use the triangle sum theorem. Add these two angles up. Subtract that from 180, and we get 20 degrees. Okay, and remember, these are congruent, these two angles, so that also means that's 120, and then that's also 40. And if that's 20, this is also 20. Okay, so we just showed that. So now we have three angles, right? So now we have angle, side, this side, and angle. So basically, we use the triangle sum theorem to show that we could also, AAS could also be ASA. Go ahead, fill that in your notes. Okay, last couple questions here. Okay, so consider what you know about the side lengths of right triangles. Okay, about a right triangle. All right. How can you use S, side, angle, side, to prove HL, hypotenuse and leg, Pythagorean theorem? Okay, so basically, if we can find this side, then that means we have side that's congruent, these two, an angle, because remember all right triangles have 90, and then we also have this side. So side, angle, side, if we can find this side. So we're going to use a squared plus b squared. So let's say this side is 9, and then let's say that this side is 15. We could find that side that's in blue. Okay, using the Pythagorean theorem, square those numbers, subtract 81. Okay, then we get 144, which then we have to square root, and we get 12. So that other side is 12. Okay, so now we know that these sides are all the same. So now we have side, angle, and side. And technically we have three sides, so we could do side, side, side as well. Okay, SSS. Okay. Go ahead and fill that in. Okay. All right. And again, just go ahead and complete your homework for section 717.